Paper 4, a 3D numerical simulation of aerodynamic characteristics of a gas filter. The purpose of this paper was to investigate ways to improve the performance of gas filters used in the ventilation systems of civil air defense engineering. The purpose of the filters is to protect against poisonous smoke, poisonous fog, biological aerosols, and radioactive dust. The paper investigates a direct flow filter, which has a complex internal design and consists of two main filter materials: filter paper and activated carbon. The large size of the filter can cause low utilization rates of the porous media, which can cause toxic gas penetration, reducing protection time and wasting energy. Researchers only have a partial understanding of experimental results, which restricts optimization. Therefore, the authors utilized the CFD to research the aerodynamic characteristics and the flow field of the filter, thereby improving the utilization rate of the filter materials. Because there is limited existing research on the aerodynamic behavior of gas filters, this topic is worthy of further research.
So how they did it. They governed equations using the 3D Reynolds mean Navier-Stokes equation shown. Since an RFP 1000 gas filter is used, the flow rate of 1000 meters cubed per hour and the Reynolds number of 78,000 were used. And since air is the gas in study, the density and viscosity values shown. Air age is used to investigate aerodynamic behavior within the gas filter. Air age is the average time a fluid particle takes to reach any point of the domain from the gas filter inlet. A higher air age means eventually leads to dead zones within the flow. Air age is calculated with the equation on the slide. The boundary conditions used were constant volumetric flow rate and pressure at the inlet and the no-slip condition at the walls. The CFD algorithms used were fluent and couple. For the CFD simulations, a simplified filter layer was used, and both porous layers are homogeneous and isentropic. The difference between Model A and B is that the Model A was created without an explosive-proof plate and Model B includes it. Pressure drop of the gas was mainly found from the filter paper and activated carbon. The equation on the slide was used to describe momentum dissipation within the filter. Alpha and beta values were consistent with the references given and therefore concluded the values as displayed for the filter layer and the activated carbon layer.
The CFD simulations were performed to determine the effects of the explosion-proof plate on the airflow and air age in the gas filter. Of note are the specific effects of the air age in the different porous media layers, the filter paper and the activated carbon. Figure 4 for the airflow shows streamlines in different models where red shows the highest flow velocity and blue shows the lowest. The explosion-proof plate shown in figure 4b improves the performance of the gas filter by reducing large backflow vortices, increasing the flow velocity, and reducing the dead zones present without the plate. The explosion-proof plate shows more benefits within the air filter paper layer at the top of the gas filter. Without the plate, there is very low air age in the center of the filter paper, which leads to penetration of poisonous gas. And there are dead zones in the corners. The plate leads to increased air age and reduced dead zones, which both improve the utilization rate of the filter paper, thereby reducing the penetration of poisonous gas. In the activated carbon layer, the plate has little effect. In both cases, the upstream section has low air age, which, as mentioned earlier, can lead to penetration of poisonous gas. The downstream section has very high air age, which is indicative of dead zones. These both indicate low utilization, which could lead to poison penetration. In conclusion, the paper looks to determine the effects of the explosion-proof plate on the performance of gas filter. The plate leads to improved performance in the filter paper layer and the overall performance, but does not improve the poor performance of the activated carbon layer. The authors indicate further optimization is required for other components of the filter.